Today's lesson stems around the most important topic in the discussion of energy, and that is the law of conservation of energy. The law of conservation of energy states that energy is neither created nor destroyed. When energy is transformed from one form into another, no energy is lost. You must think of this law of conservation of energy whenever you look at any energy transformation question. We're going to take a look at a diver that starts off at the top of a 10-meter high diving board. He's then going to fall off and fall towards the water. During this time, there will be an energy transformation that is taking place. But during the entire dive, it is important to remember that the total energy will remain constant. And we know this because of the law of conservation of energy. So we'll look at the dive in 3 stages. We'll look at before he dives while he's waiting on the top of this 10-meter high platform. We'll look at the halfway point where he is 5 meters from the water. And then we'll look at just before he enters the water. So where his height above the water is 0. So at some point, we would like to calculate the total energy that this diver possesses. And we know that if we can find the total energy, that value will remain constant throughout the entire dive. So let's see if we have enough information to calculate the total energy in phase 1, just before the dive, while this diver is resting at the top of the platform. So we know that the total energy is equal to the sum of all the energies. So let's see what types of energy we have. We've studied 2 types of energy. We've studied gravitational potential energy, which is a result of an object's position above the ground, and we've studied kinetic energy, which is a result of an object's speed. So at this position, I want you to ask yourself whether the object possesses gravitational potential energy. So the real question is, does the object possess height above the ground? And the answer is yes, so therefore the object possesses gravitational potential energy. While this object is, or this person is at rest, at top, we ask if they have any speed. And the answer is no, so the object does not possess any kinetic energy. So all of his energy is gravitational potential energy. And we can calculate the total energy using the equation for gravitational potential energy, which is mg delta h. Subbing and solving, 65 kilogram, 9.8 newtons per kilogram, and a height of 10 meters. The total energy, 6.4 times 10 to the power of 3 joules. Now this is important. If you know the total energy while this diver is at the top of the diving board, you will know the total energy of the diver at all of the stages. So this total energy is the value of the total energy at the halfway point, and it's also the value of the total energy at the water surface. In phase 2, at the halfway point, we want to determine the speed of the diver at this halfway point. And we're going to use the law of conservation of energy to allow us to find it. We're going to start this question the way we did before, and we're going to list all of the different types of energy present. So the total energy is equal to the sum of all the energies. At the halfway point, the diver is above the water. He's 5 meters above the water. So as a result of his height above the water, he has gravitational potential energy. But he's falling towards the water with speed. So as a result of his speed, he also has kinetic energy at this stage of his dive. So we can start subbing in. We know that the total energy is 6.4 times 10 to the power of 3 joules. And that is equal to the gravitational potential energy at this stage plus the kinetic energy at this stage. So mg delta H for gravitational potential energy and mv squared over 2 for kinetic energy. And your job is to solve this for V. So we need to rearrange this equation and solve for V. First thing we'll do is we'll bring this mg delta H over the equal sign. So we get 6.4 times 10 to the power of 3 joules minus mg delta H equals mv squared over 2. Next, we will attempt to isolate that V, get it by itself. So we'll have to address the 2 in the denominator. In order to get rid of that 2, we can multiply both sides by 2. Then we'll have to get rid of the m in the numerator. In order to get rid of that m, we'll divide both sides by m. So we'll get V squared is equal to 6.4 times 10 to the power of 3 joules minus mg delta H times 2 divided by m. So we can sub and solve, and we know that V is equal to the square root of 2 times 6.4 times 10 to the power of 3 joules minus 65 kilograms times 9.8 newtons per kilogram. And at this phase, we're at a height of 5 meters above the ground. And the mass is 65 kilograms. Carefully take your time, punch this into your calculator, and determine the speed of the diver at the halfway point. To 2 significant digits, you end up with a speed of 9.9 meters per second. In phase 3, how much energy does this diver possess just before he hits the water? Well, the total energy is going to remain the same, as it has been for the entire journey. It's 6.4 times 10 to the power of 3 joules. But what type of energy does it possess? Let's start by listing all of these types of energy. So, total energy is equal to the sum of all the energies. So at this point here, the diver has no height above the water. As a result, he has no gravitational potential energy. He started off with all gravitational potential energy, but now has converted it all into kinetic energy. So all of the 6.4 times 10 to the power of 3 joules of energy has been converted into kinetic energy, mv squared over 2. And we can use this relationship to determine the speed of the diver just before he enters the water. All we have to do is solve for V. So we have to get rid of the 2 in the denominator, and we do that by multiplying both sides by 2, and then the m in the numerator, so we'll divide both sides by m, and make sure you take the square root of both sides. I'll do this all in one step, and as you get more proficient, you'll be able to do the same. So we have 2 times 6.4 times 10 to the power of 3 joules divided by a mass of 65 kilograms. Punch it into your calculator, and to 2 significant digits, you end up with 14 meters per second. So we found the speed with which this object, or the diver, enters the water. Now we could have solved this using kinematics equations from Unit 1. So we know that an object is free falling, accelerating at a rate of 9.8 meters per second squared, with an initial velocity of 0 over a distance of 10 meters. And we would have been able to get this exact same answer. But instead of using that information, we're using the law of conservation of energy to find the same value.